Hello and welcome to comp452 computer architecture. So let's design the controllers now. So today we are first going to talk about ALU controller, ALU controller, and after that we will talk about main controller. Then we will talk about main controller. Because ALU controller is simpler to design, so that's why we will design it first. Okay. How many control lines our ALU has? If you remember, our ALU had 4 control lines. 4 control lines. And if you look at the table or the diagrams in Appendix B of your textbook, Peterson and Hennessy, you will see that they were B invert, A invert, and then op1 and op0. And if you remember, these were select lines of mux. Okay, we had a 4-to-1 mux, and these two, as their names indicate, they negated the value of input A and B. Okay, so these 4 were the control lines of our ALU, and I'm just reproducing the table. I think the table is given in figure B dot 5.13, if I'm not wrong, but you can look it up in your textbook. And so ALU control lines, okay, and then here we have functions, the function that they perform. So if all 4 lines are 0, our ALU will perform AND operation on the 2 values input. If it's if it's 0 0 0 sorry 0 0 0 1, then ALU will perform OR operation, and if the value of the control lines is 0 0 1 0, then we will have add function, add operation. For 0 1 1 0, we have subtract operation, and if it's 0 1 1 1, then we have set on less than operation, and finally if it's 1 1 0 0, then it's a NOR operation. Now I have just reproduced this table from your textbook. If I'm not wrong, it's given in it's given on page 140. It's given, I don't know the page number, but it's given in figure B dot 5.13. So ALU control lines, ALU CTRL means control lines. Okay. All right. So now, who is going to control these four lines, and how these four lines are going to be controlled? That's what we want to ask. Who controls these four lines and how? Now the first part is very easy. Main controller controls these lines. So answer to the first part is main controller. And this answer to the second part needs a little bit more discussion. Actually, I shouldn't have said that main controller controls these four lines. Actually, this is not correct. So let me erase it. This is a very misleading statement. It's a very misleading statement. So I take back my words and I say ALU controller controls these four lines. That's the correct thing to do. Now ALU controller is a combinational circuit. Okay, so let's draw a block diagram. This is a block diagram. This is ALU controller. This is ALU controller, and the output of the ALU controller are these four lines, and these four lines go to ALU. So these are outputs, okay, outputs of ALU controller and inputs of ALU, right? So outputs of ALU controller and inputs of ALU. Okay, now what will be the input of ALU controller and how many lines will we need? How many lines are we going to need? 1, 2, 3, 4. How many lines? Okay. It turns out that okay, by the way, how do we determine the number of input lines? How do we determine the number of input lines of ALU controller? That's the question that we want to answer. These four output lines, they will be 4 because the ALU that we want to use has 4 input control lines. So the ALU controller output lines will be 4 in number, at least 4. Okay. But how many input control lines should we have for our main for our ALU controller? That's the question that we need to ask or maybe answer. Okay, so let's see how the instructions that are executed by our MIPS processor implemented, how they are implemented, and that will tell us how many input control lines we need. Okay, Now here the most important thing is that most important, and let's write it in red color. Most important. Most important, since it is actually most important, so that's why we have written it in red. All R type instructions have opcode 00000. All R type instructions. Okay. So the opcode, the opcode is a 6-bit field in the instruction. Okay. Opcode is a 6-bit field in each and every MIPS instruction. Okay. So all R type instructions have opcode of 00000. Good. So it means the instructions that our MIPS processor is implementing, which is AND, OR, NOR, AND, OR, NOR, add, subtract, and SLT. All these instructions will have an opcode of 0. All 6 bits will be 0. So how will our ALU controller determine the instruction? Main controller, basically the point is that since opcode bits are all 0 for all R type instructions, so there has to be some way of knowing which operation to perform. Okay, there has to be some way of knowing which operation to perform, and if you remember, there is a 6-bit function code which tells us the operation that has to be performed for the R type instruction, for any R type instruction. Now all the opcode bits are 0 for all R type instructions, but function code bits are not 0. So it is the function code bits that will tell us which operation has to be performed by the ALU, and therefore all these 6 bits must be available to the ALU controller to determine how to configure or set its output lines so that correct operation is performed. Okay, so all these 6 bits, they must go to ALU controller input. ALU controller input. They must go to ALU controller input. So that I'm not writing that. So that ALU controller can correctly set its output lines, and ALU performs correct operation. So we have determined that our ALU controller will have at least 6 inputs. Okay, so those 6 inputs will be 6 function code bits. This is must. Now we need to figure out, do we need any additional input lines? I'm sorry, I'm drinking my green tea kahwa. You can also bring your green tea kahwa and listen to this lecture. or whatever you like. Okay, it's quite refreshing in winter. Actually, for me, it's also refreshing in summer. So we have determined that we need at least six inputs to ALU controller, at least six. Now, in addition to the R-type instructions, we also have a few I-type instructions that our processor needs to implement. And what are those I-type instructions? They are load word and store word and branch if equal instruction. Okay, very good. So in these R type instructions, all function code bits are 0. All function code bits are 0 in I-type instructions. I-type instructions. I'm sorry, somehow this all I-type instructions. So it means that we are probably going to need more inputs. Why? Okay, so here is the thing. When processor is executing load word or store word instruction, for load word or store word, we want we want ALU to perform addition operation, add operation to calculate the address, to calculate data memory address. Why? Because if it's a load word instruction, we need to calculate the address of the memory location from where we want to read data, and for store word instruction we want to calculate the address of the memory location in data memory where we want to write value of a register. Alright, good. And for branch if equal instruction, we want ALU to perform subtraction operation to find, actually not to find but to determine, my English is very poor, to determine if the values in the two registers are equal. Alright, so it means that for I-type instructions we need to perform addition for load word and store word and subtraction for branch if equal instruction. So these are not R-type instructions. For these the function codes will be 0. So since the all function code bits are 0 for I-type instructions, so the 6 inputs of function code that go into the ALU controller, they will all be 0. So we need a way to determine what to do in such a case. Okay, so in that case it means we need to have at least one input, at least one additional input, and if that input is 0, then we will be doing one operation, and if it's 1, then we will be doing the other operation, and those two operations are add and subtract. Okay, so instead of having just one additional input, what we do is we introduce two additional inputs. We introduce two additional inputs. Okay, and we call those two additional inputs. We are going to let's write here. We introduce two. Oh, I'm sorry. We introduce two more inputs to ALU controller, not the ALU. ALU has only 4 inputs. But for ALU controller, we introduce two more inputs and call them ALU. ALU op1 and ALU op0. Okay, so we introduce two more inputs. So now how many inputs do we have in total? We have 8 inputs. 6 of them are function code bits, and the remaining 2 are ALU op0 and ALU op1. Now the question is, who is going to control ALU op0 and ALU op1? Who controls these lines? Okay, now the answer is ANS. Answer is main controller. So main controller is going to control these two lines, and they will be output of main controllers. These lines, they will be output of the main controller and input of the ALU controller. And the other 6 inputs will come from the 6 function code bits. Now the function code bits are already present in the instruction itself. Okay, they are present in the instruction itself. Okay, so with this, now we are in a good position to move further. Actually, we have run out of the first page, and let's go to the next page, and let's set the zoom to 100%. Let's lock the zoom. Okay, now we have 8 inputs to our ALU controller, and those 8 inputs are ALU op1, ALU op0, and then we have 6 function code bits, F5, F4, F3, F2, F1 and F0. These are the 6 function bits. So these are the inputs, and we know that the outputs are 4, and let's call them operation bits, and here we write operation name. These are operation bits. So now we have to decide on the values of these two input lines. Okay, these 6 lines we do not have we do not have any control over these 6 lines, over these lines. Who controls these lines? Who controls these lines? There we go. Let me write it in a MIPS consortium controls these lines. So their values will be specified by the designers of the MIPS instruction set architecture. We do not have any control over these 6 lines. These 6 lines, we don't have any control. We will just look it up in the MIPS specification document. But these lines, ALU op 1 and ALU op 0, they are in our control. These 2 lines, this line and this line, they are under our control. So let's say that we say that, okay, if we have to perform addition operation for load word and store word, if we have to perform addition operation for load word and store word, then we will set both of these lines to 0. For load word and store word. Now for load word and store word, our controller, ALU controller, will not look at these 6 bits because it will know that it's not an R-type instruction. And these 2 lines, we decide that when ALU op 1 and ALU op 0 are both zeros, then the operation that we want to perform is addition operation. And addition operation, the output lines will be 0, 0, 1, 0. Output lines will be 0, 0, 1, 0, 0, 0, 1, 0, and this will be add operation, and in parentheses I am going to write for load word and store word instructions. I'm sorry for sneezing. So this is now this we have decided. This is under our control, these 2 lines. Okay, so now for load word and store word, we'll set the ALU op bits to 0 and 0. And let's say that when this bit is 1, once again we do not look at the function code, but we will perform subtraction operation, and this operation will be done for branch if equal instruction. Now keep in mind that this ADD is not the add instruction, it's the add operation of ALU. This SUB is not the subtraction instruction, it's the subtract operation performed by ALU. The instructions are a branch if equal or load word or store word. So now this is our decision. I could have made it other way around, that if ALU op 1 is 0 and ALU op 0 is 1, then we perform add operation. And if ALU op 1 is 0 and ALU op 0 is also 0, then we perform subtract operation. We could have done that because it's in our control, okay? But we didn't do that because your book is doing it this way. So we make this X, do not care. So if ALU op 0 bit is 0, okay, then we look at ALU op 1 bit. If it is also 0, then we simply perform add operation. We do not look at the function code values. If ALU op 0 bit is 1, then regardless of the value of ALU op 1 bit, this ALU op 1 bit, we simply program our ALU to perform subtraction operation, because we know that it's going to be a branch instruction, branch if equal instruction, okay? Now we say that if ALU op 1 bit is 1, then we don't look at ALU op 0 bit, but now we want to look at the function code bits, okay? We want to look at the function code bits. And now for and or nor SLT, add and subtract, these are the R type instructions. For AND R type instruction, what I am going to do is I am going to look up the value of function code bits as specified by MIPS designers, okay? So what I am going to do is, let me tell you what I am doing right now. I am typing in Google op code bits, MIPS op code and function. Okay. Actually, why not MIPS function codes, and there we go. Actually, it's given in your book, but I just want to drink my kava. So I said, okay, I'll look it up in the PDF document. The PDF document is not showing me anything useful, so I say it, you are useless. So by the way, there's no need to remember these function codes. Okay. Now for AND operation, the function code bit is hex 24. So hex 24 means 0, 1. I'm sorry. This is 24 in hex. Now what we want to do is we want to do, what should be the output for this input combination? It should be the bits which program ALU to perform AND operations. So from our table on the previous page, look, all 4 output lines of ALU controller should be 0, and that's what we have written here. See, that's what we have written here. Now let's see what is the function code for OR operation. Function code for OR operation, and function code for OR operation is hex 25. So this is 1, this is X, and hex 25, 2, and 5 is 101. Oh, I'm sorry, 101. Now we want to perform OR operation. So let's go back and see. This is the these are the ALU control lines for OR operation 0001. So we come here and we write 0001. Now let's look at this NOR operation. And NOR operation, the function code is hex 27. Function code is hex 27. So hex 27 means this is hex 27. And what will be the output bits for NOR operation? 1100, 1100. So 1100. Now let's look at the opcode for SLT. Opcode for SLT is sorry, not the opcode, the function code. Sorry. Once again, very sorry. The function code for SLT instruction is 2A. So we write 1 here, we write X here, 2A. A is 1010. And now let's go back and see what we need to do for SLT. 0111. 0111. Okay, now let's look at the function code for add. Function code for add is hex 20. Hex 20. So this is hex 20. And now let's go back and look at our in our table. For add output, the ALU control line should be 0010. So we come back here and we say 0010. And finally, the opcode for subtract, SUB, opcode for subtract is hex 22. Hex 22. Hex 22. And we go back here, and what should be the bits for subtract? 0110. So we come here and we write 0110. Let me actually erase this 0 and rewrite it. Oh, sorry. 0010. Okay. Is this good? So now everything on the left of this double line is input, and these 4 are the output lines or outputs of ALU controller, and these are inputs of ALU controller. So we have a combinational circuit. We want a combinational circuit with 8 inputs and 4 outputs. Now it's not difficult to design. You can give this whole truth table to software tools which will simplify this this truth table, and actually it's in simplified form. The input to the tool would be this truth table, and the output of the tool would be a circuit which implements this truth table, and that circuit will be called your ALU controller. Okay, that circuit will be called your ALU controller. Okay, so we have designed our ALU controller, and next we would like to design the main controller. Okay, and I'm just going to show you a figure, hoping that I have it. I have it here, and I am pretty sure that I have it here, but I'm going to pause the recording for a few seconds. Okay, so I want to show you this data path, updated data path with ALU controller. So I am going to insert a PDF, and this is the PDF that I want. Let's make the zoom 100%. Let's lock it. Okay, so this is our data path, and you see I have introduced this ALU controller. Look, these 6 bits, these are the function code. They come from the least significant 6 bits of the instruction, bit 0 to 5. They are going to the input of ALU controller, and these are actually 2 bits or 2 lines. Actually it's better if I write 2 lines, and these lines will be coming from main controller. And look, this is the output of the ALU controller, and this output is going to the 4 inputs of the main ALU. Okay, and this is our ALU controller. It's a combinational circuit. Okay, so this is what I wanted to show you. Actually it's figure 4-15 of your book. This is figure 4-15 of your textbook, Patterson and Hennessy. Alright, so we have completed our discussion of ALU controller, and next thing that we would like to do is work on the main controller. So I'm going to stop here, and there we go.